We're going to take a look today at section 2.8, which is complex fractions, and it's actually not that much different than we did before on another lesson. It just looks a little different at the outset. So we're going to take a look at division. We've talked about division from this perspective as well. Division being the same thing as multiplying by the reciprocal. So when you guys saw things like this before, it looked like, like 4 over 3 divided by x over x minus 3 or something like that. And all we did is we took the second fraction and we did what? Yeah, we flipped the second fraction. So we kept the first part. We changed it from division into multiplication, and we flipped it upside down. Do you remember that?
Yeah.
Okay. So the only difference in what we're doing today is how it starts looking at the beginning. Instead of it looking like this, it looks scary because it looks like this. The problem starts out looking like fractions inside of fractions. But they're not any different than having them being written as division. Okay? They're not. There's a little bit of a caveat to that. It's toward the end, and I'll show you what happens there. But not toward the end. It's actually showing up in example number 3. We'll see it. But what we really have happening here is we really have just division of fractions. All right, so far so good?
Yes.
Okay, so the first problem just looks like that. It's just numbers, in fact. And if it helps you to see it written this way, I would encourage you to do so. Just rewrite it as division by 3. So as you see these, you're going to see one of the fraction bars look a little bit longer or darker. It's going to be very clear where the two fractions are splitting. This is not 5 divided by 3 divided by 3, right? The size and the font and all of that kind of stuff dominates, and you'll be able to tell. But this actually changes into multiplication by...
Sorry, what? Reciprocal.
The reciprocal. And what's the reciprocal of 3?
1/3.
1/3. Okay, so 3 is 3 over 1. Its reciprocal is 1/3. So division becomes multiplication by the reciprocal. And then it's exactly what we were doing a couple of different times. We've done it back in Unit 1, and we did it 2 lessons ago as well in 2.6. Division is multiplying by the reciprocal. So what is 5 over 3 times 1 over 3? 5 over 9. We just multiply across, right? And reduce if we can. This one doesn't reduce. Okay, second one, exactly the same thing. So instead of having it written as 3 over 5 divided by 9 over 14 in fraction form, I can write it like this. And then it looks like what we've done before. The 3 over 5 will stay. Division becomes multiplication, and 9/14 becomes 14 over 9. Now, if you'd like, you can do like we done the last one where we just multiply across the top, multiply across the bottom. You can also look, just because we're dealing with fractions, across diagonals to see if things reduce. And this one they do. This 3 divides by 3 and 9 divides by 3. 3 divided by 3 is 1. 9 divided by 3 is 3. The other diagonal doesn't have any reducing. It's a 5 and a 14, right? So there's nothing I can do there. So I'm going to, at this point, be like at the point where all I can do is multiply across the top. 1 times 14 is 14. And then 5 times 3 is 15. Okay, is that all right?
Yes.
Okay. I'm going to show you 2 ways to do number 3. And then I'm going to kind of just tell you which of the 2 I think is my preference. And you can choose the other one if you want. I don't care. So one way to do this number 3 problem is to turn the entire numerator into a single fraction and the entire denominator into a single fraction, and then do the same thing we just did on problems 1 and 2. Okay? So I'm going to show you that first, and then I'm going to show you an alternative to doing that and see which one you like better. Okay? So if we take a look at the entire numerator right here, in order to get this to be a single solitary fraction, not a mixed piece, a whole number piece and a fractional piece, we need common denominators, right? So this is the same thing as having, I'm just going to do these in 2 pieces. 5 over 5 minus 7 over 5. Right? 1 is the same as 5 over 5. And we did this way back when. We just wrote it as a 1 over, and we multiplied by the 5 over 5, so we get 5 over 5. So if I have that, 5 over 5 minus 7 over 5 is what?
Negative 2
Negative 2
over 5.
over 5. We're going to do the same thing on bottom. I have 7 over 4. The 2 is over 1, so what would I have to do to get it over 4?
Multiply by 4.
Right, multiply it by 4. So 4, whoops, wrong pen. 4 over 4. This would give me an 8 on top and a 4 on bottom, and it is addition. So what is 7 over 4 plus 8 over 4?
15 over 4.
15 over 4.
We had to put it into a mixed number, or did that? Oh no, it wouldn't work because we.
Right. It wouldn't help.
Yeah.
However, we're not done. We've just done the numerator separate from the denominator, right? And then we have to actually do the division. So I have negative 2 over 5, and it is divided by 15 over 4. And I'm back to the same thing I did on problems 1 and 2. So negative 2 over 5 times 4 over 15. If I compare along my diagonals, they don't simplify this time, do they? They don't. So multiplying straight across the top, what do I get? Negative 8. And straight across the bottom, I get 75. There's nothing wrong with this approach. It's perfectly reasonable. It relies on a lot of prior knowledge. We've done every step of that before, and now we're shoving it all into one problem. However, there is an easier way to do the problem. You game for that?
Does it involve trial and error?
No, it does not involve trial and error. It's a good question. Okay, so I'm going to clean up the work that I did like on top of the problem so that we can see the problem fresh again, okay? So this approach right here, I won't delete it, whoops, but I will shift it up and make it a little smaller. Okay, approach number 2 says, look at the tiny little denominators. What are my 2 tiny little denominators? 4 and 5. Everybody good with that? You see the tiny little denominators. And we will find the least common denominator of the 4 and the 5. Well, 4 and 5 don't have anything in common, so the least common denominator would be the multiplication of them. It's 20. Okay, you could also say least common multiple. That might make more sense because of the way I've taken them out of the denominators. Let's go with that, least common multiple. So if I look at multiples of 4 and multiples of 5, the first multiple they have in common is 20. Yes? Okay. Here's what we do. We take 20 and we multiply it by every single piece in our problem. Every piece. Not just the ones with the denominators, not just the ones without. Every single piece. Okay, so what have I really done? Well, I've really just multiplied the numerator by 20 and the denominator by 20. I'm allowed to do that. Multiplying by 20 over 20 is equivalent to multiplying with the number 1. Why is it helpful? Well, take a look. 20 times 1, that's fine, it's 20. But what happens when I multiply it into 7 over 5 times 20? Blank stares. Okay, let's try it. 20 is the same as 20 over 1, right?
Yes.
The denominator, 5, and the 20 will reduce. What's 20 divided by 5?
1 over 4. Or
4.
yeah.
Every time I use the correct multiple, right, an actual multiple, even if it's not the least common multiple, all the little denominators are going to cancel out. So I now have 7 times 4, which is 28. You can do the same thing here with this 20 and this 4. What's 20 divided by 4? 5. So the 4 cancels because 20 divided by 4 is 5. And what's 5 times 7?
35.
35. Y'all are having me worried there for a sec. 35. And the last part is just multiplication of integers, right? 2 times 20. What is 2 times 20? 40. 40. The beautiful thing about this approach is that your little denominators, right, the fractions inside of fractions go away very quickly. I'm left with 4 numbers. They're all integers. There's no fractions involved in the individual components. What's 20 minus 28?
Negative 8,
And what's 35 plus 40?
75.
And sure enough, we got the same answer.
Pretty nifty.
Okay, are you with me? Okay, that's the approach that I'm going to keep working with because it's quicker, because it cleans things up faster. If you don't like that approach and you want to do what I did the first time, that's fine. You can do it. There's nothing wrong with it. It's just more steps. So, at this point on number 4, I have 4 denominators, 4 little denominators, right? Some of them are repeats of each other. They aren't all unique. So what are my 4 different denominators that I have? 2, 4, 5, and I don't really need to list the 2 twice, so I don't, right? 2, 4, and 5. Think about multiples of 2. So I've been working with one of the kids in my house recently about like counting by 2s, right? 2, 4, 6, 8, 10. Those are the multiples of 2. Multiples of 4. 4, 8, 12, 16, 20, right? Multiples of 20, just 4. And then we have multiples of 5. 5, 10, 15, 20. What is the first number that they all share in common as a multiple?
20.
It's 20. I promise the answer is not always 20. It just has been on number 3 and 4, okay? Not always 20. This number, 20 here, now gets to be multiplied by all 4 of my little fractions. So I'll do it in red. Because each of the 4 pieces, unlike the last problem, are actually fractions, each of those 20s is going to reduce, right? So this 20, the first one, is going to be divided by 5. What's 20 divided by 5? 4. So these 2 become a 4. And I'm left with 4 times 6, which is 24. Second piece. I have this 20, and it's divided by 2. What's 20 divided by 2? 10. There's a sign that's negative in between. And now I have 5 times 10 to give me 50. I have another 20 and 2 down here, so 20 divided by 2 is again 10. But this one is 3 and the 10, so 3 times 10 is 30. I have subtraction on bottom as well. And then the last one is 20 divided by 4, which is 5. And I have 5 times 5, which is 25. No more double fractions, just like that. Now we've got arithmetic, right? Dividing and, subtracting and then dividing if we can. What is 24 minus 50?
26, negative 26.
Mm-hmm. And how about 30 minus 25? Yep. And I think it's negative, right? Oh, no, it's positive. Sorry, I got my numbers backwards. It's 5. 26, 5. Do they have anything in common? No. So we're done. Okay, so far, all 4 of the first 4 problems have been just numbers. Some of the problems you work with are going to be just numbers. But some of them are also going to have variables involved. But the good news is when the variables are involved, the process doesn't change anything. It still works the same way. So this problem looks a lot like problems 1 and 2. Right? Fraction on top, big division, fraction on bottom. So this is actually exactly the same as having it written. So this is x plus 4 over x minus 5 divided by the denominator fraction, which is x plus 4 over 5x to the 4th. Okay, this is just like problems 1 and 2. What do I do when I have a division of fractions?
Keep, change, flip.
Keep, change, flip. So we're going to keep the first one. We're going to change the multiplication, change the division to multiplication, and we're going to flip the second fraction. just like problems 1 and 2. And what do you notice happens?
Cancel out.
What cancels?
4x.
Okay, the x plus 4s, yeah. The x plus 4s cancel. I know the other diagonal has x's on it and 5's on it, but it doesn't have factors of x and factors of 5 on both pieces, right? One of them has terms. So there's nothing I can do to cancel along the other diagonal. So if I multiply across the top, I have 5x to the 4th. And across the bottom, I have x minus 5. And the same thing's happening on this one, right? Fraction over fraction. Now, if you can do so, you are welcome to jump straight from here to here. Don't have any problem with that. If you want to see the in-between step where I've written division, by all means show it. So it's your call. I'm going to continue to show it for those who might want to see it. And if you don't want or need or care to see it, then just don't show it. This is 2x minus 10 over 2. So just like on the previous one, first fraction stays the same. Division becomes multiplication, and the second fraction flips upside down. 2 over 2x minus 10. Now, unlike the last one, at first glance, there doesn't really seem to be anything that's going to divide out. But I do have 2x minus 10. It's a little bit different than I had before with the x plus 4s and so forth. So 2x and 10 actually have a common factor themselves. What common factor do they have? 2. So I can rewrite the second denominator. I'll do it in another step. Again, you don't have to do it in a separate step. But I can pull out 2 out of the denominator. If I pull a 2 out of 2x minus 10, what am I left with?
X minus 5.
X minus 5. Very good. Now, you can look either across diagonals, and you can cancel like the 8 and the 2, or you can look within a single fraction and cancel the 2 and the 2. It doesn't make any difference. I'm going to do it within the same fraction on mine. The 2's are going to cancel. But looking at the other diagonals or the other fraction, there's nothing else that reduces. So all I can do is to multiply across the top. So I've got 8 times 1, or 8. And across the bottom, where I've got a 5x and an x minus 5. Is that okay? Seven, fractions and fractions, right? So this time I am going to jump to the second step of the problem. If you want to show the in-between step where we wrote the division piece out, feel free to do so. So I've got the first piece, and I'm going to jump straight to multiplication. It's going to be the multiplication of the reciprocal of the denominator, which means the x minus 2 is now in the numerator, and the 4x minus 28 is in the denominator. Like the last one, the first numerator and the second denominator have pieces that will factor out of them individually. 7x and 49 are both divisible by what?
7.
7. So I'm going to rewrite the first one by pulling out the 7. If I pull a 7 out of 7x, I get, of course, x. What about a 49 and I pull out a 7?
7.
I get another 7. X minus 2 on top. How about the denominator 4x minus 28? Pull out a 4, and I'm left with x minus 7. Okay, so looking across diagonals, looking within individual fractions, what do you notice that will reduce?
X minus 7.
You bet, x minus 7s. And it's the only thing, actually, isn't it? It doesn't look very good. So at that point, there's nothing else I can do except to multiply straight across the top. Now, while it's not bad if you want to distribute the 7 to the x minus 2, it's also not necessary. I'm perfectly happy for you to leave it written as 7 times x minus 2 and leave the denominator written as the 4x. You do not need to distribute them out. In fact, in factored form, I can see at a glance, it is reduced as far as it can go. If you multiply it back out, we both have to stop and think, is it reduced as far as it can go? And here we know. Okay, our last one. This problem looks like 3 and 4. Look back at 3 and 4. Doesn't it? I've got some pieces that have an extra denominator, right? And some pieces that don't. But this denominator is way easier to do than 3 and 4 were. Because the little denominators are actually the same, aren't they? So if I'm trying to find the least common multiple of simply w, because that's the only thing there is, it's just w. So what does that mean in terms of my problem? Well, it means that instead of multiplying by 20 on all the pieces, like I did in those other two examples, I just multiply by w on all the pieces. The first one, when I multiply w by 2 over w, what happens to the w's? Yeah, they just cancel out. And I'm left with 2. The next piece, it's just 7 times w, or 7w. All right, this is running into it. Let's move it down a little bit. The third piece, which is the w and the 3, again, just get multiplied, so that's 3w. And what happens to the 2 over w and the w? The w's just cancel out, leaving me with 2. There's nothing in common on the top that I can factor out. There's nothing in common on the bottom that I can factor out. So I'm done. So, as unlikely as you thought it might have been, this problem with variables is easier than 3 and 4 that didn't have them, isn't it? Because the variable itself was the only denominator.